right, so let's look at this. Look at this question from WAEC 2022. It says 3 cells, each of EMF 1.1 volts and internal resistance 2 ohms, are connected in parallel across a 3 ohm resistor. Determine the current in the resistor. Okay, so this is the diagram. You can look close in there. So it's 3 cells, symbol for cells, 3 cells in parallel. Of course, this is the connection, and they have each 1.1 volts and internal resistance of 2 ohms each. So that's what it looks like, right? And they are connected in parallel to an external 3 ohm resistor. Alright, so now let's to solve this question, we have to use the formula that connects. Remember the formula that connects internal resistance, small letter R, external resistance R, current, and EMF. So for cells in parallel like this, the effective EMF is the EMF of one of the cells. So we're going to use 1.1 volts effective EMF. And for cells in parallel, of course, do our total resistance parallel inverse. So you do that with the LCM of 2, then you have 1 plus 1 plus 1, so you just add up 3 over 2. So you get the 1 over R total is 3 over 2. So R total is the inverse of 3 over 2, which is 2 over 3, and that's 0.67 ohms. Alright, so we've calculated the internal resistance, the total effective internal resistance for the 3 cells. Okay, so we'll now put that into this formula. This formula that helps us to determine the current in the resistor. Alright, so this formula, making I the square with the formula, we can make I the square with the formula. So E will divide the sum of the external and internal resistance here. So I is like this. So putting your values 1.1 over, remember the external resistance is the resistance across this resistance here, 3 ohms. So that's a capital letter R. So put that into this expression, 3 plus 0.67, and you get 3 amperes, 0.3 amperes. Alright, so let's talk about galvanometer conversions. There are ways we can convert galvanometer to, a galvanometer measures only small currents, but the galvanometer can be converted into an ammeter to measure larger currents. Galvanometer measures currents in milliamperes, while an ammeter measures currents in larger values like 1 ampere, 2 amperes, and the likes. So how do we do that? By placing a small resistance in parallel with the galvanometer. So this small resistance in parallel is called a shunt. So this looks something like this, in parallel with the galvanometer. So this shunt diverts the current in excess of the galvanometer. Okay, so let's consider this example. We want okay, like I said, that the galvanometer, this is our galvanometer. It can only measure, it has a full scale deflection of 50 milliamperes. Okay, and we want it to be able to measure current of 2 amperes. So what's going to happen is 50 milliamperes will pass through, and the larger current of the remaining current, if you subtract 50 milliamperes from 2 amperes, you're left 1.95 amperes. Okay, and so the 1.95 amperes will be diverted through this smaller resistance. Okay, because the smaller the resistance, the more current can pass through. So this is our shunt. Okay. Alright, so basically we're just taking advantage of our knowledge of resistors in parallel, alright, and the fact that the smaller the resistance, the more current it can allow through. So this galvanometer can only take a current of 50 milliamperes. This is about 0.05 amperes. Okay, and has this internal resistance. So the question is, let's calculate the value of the resistance, the value of the shunt, which will be able to make this 2 amperes possible through this setup. And so remember that they are at the same potential difference, between these wires. Alright, so the key is that the potential difference between the ends of this, our shunt, okay, this our attached resistance, is the same potential difference between the ends of this our galvanometer that we are trying to adapt. So this setup, they go together. So it's going to adapt this galvanometer to be able to pass this current, but of course it's not going to pass all of the current. Much of the current will be passed through this, so they go together. So the potential difference across the shunt is across the galvanometer is the resistance times the current. Remember, V is equals IR. So make R. Okay, so we just have this equation because they are the same potential difference. So for our galvanometer, we multiply this together. So for our shunt, current times resistance, we are looking for this particular, the value of the shunt. So R is our unknown. So divide both sides by 1.95 and you get that your answer is the value of the shunt that is needed to make this galvanometer, to adapt this galvanometer to this huge current is 0.128 ohms. Thus, a small resistance shunt of 0.128 ohms will convert a galvanometer into an ammeter reading up to 2 amperes. Alright, so to convert a galvanometer, conversion to a voltmeter. How can we convert a galvanometer to a voltmeter? So we use a high resistance multiplier. Okay, so the term is called a multiplier, high resistance wire, okay, in series with the galvanometer. Okay, should place in series with our galvanometer. So let's consider a galvanometer whose full scale deflection is 10 milliamperes. All right, and it has an entire resistance of 5 ohms. The potential difference across it, V1, is going to be calculated as 0.01 times 5. Remember, we're getting 0.01 from 10 milliamperes. Convert this to amperes, you get 0.01. So times this, so that's the voltage. Alright, so this is what it looks like. It looks something like this. So this is our galvanometer. It has an internal resistance of 5 ohms and it can only pass only a current at full scale deflection. It can only pass 10 milliamperes. Alright, so this is what it now. So you get a multiplier, you get a resistor, a huge you get a resistor. So the resistor is going to pass, remember they are in series, so the current that is passing through this resistor is the same current that will pass through our galvanometer. So since the same current flows through both resistances in series, and you know that resistors in series splits the voltage in two. Alright, before we continue, I must say that what we are trying to do here, we're trying to adapt our galvanometer into a voltmeter. So we can adapt it, we want to adapt it to read voltages of up to 20 volts. That's why you have this 20 volts here. We want to be able to read voltages to up to 20 volts by using this setup. Okay, so 20 is 20 volt, and this is our multiplier. Okay, is in series. A high resistance in series with our galvanometer is called a multiplier. So it's going to split this 20 volts. So I know that our galvanometer can only take 0.05 volts. We just calculated it from here. That's current times. Alright, so we've calculated. So this the galvanometer is going to take voltage of V1. So V1 is basically, remember from Ohm's law, V is equals IR, that's current and resistance. So the current is taken is 0.1. So at full scale deflection, you can only take 10 milliamperes at full scale deflection. So 10 milliamperes is 0.01 amperes. So we calculated V1 as 0.05 volts there. So that means that our multiplier can take the remaining out of 20 volts. So subtract that, you get our multiplier can take 19.95 volts. Okay, so this V2 is 90. So divide it by 0.01 amperes. Alright, so our 0.01 amperes here, 0.01 amperes is current that usually is common current. Okay, they are in series. So the same 0.01 amperes that flows through our galvanometer is what flows through our multiplier. Okay, that's our our resistor in series that helps us to adapt this galvanometer into a voltmeter that can read up to 20 volts. So do your division. So voltage over current gives us the value of the multiplier resistance which we need, which is a huge value, 1995 ohms. So a multiplier of 1995 ohms is needed to convert the galvanometer into a voltmeter to read up to 20